So welcome everyone to the Berlin Functional Programming Group again. It is beginner's night in the Berlin Functional Programming Group because we have a talk on ATS, which is, my understanding is the very beginner-friendly approach to functional programming for those who aren't familiar with it. And we scoured the globe looking for the most preeminent speaker on this topic we could find, and he's with us tonight. I'm trying to remember when I first learned about Aditya Siram, who everyone knows as Deech, and I feel like he was always there. Somehow he ended up in my Twitter feed, and I have to say that he does very good Twitter, and I always found him very interesting and entertaining. I don't know when I even knew about the ATS connection, but I watched his videos on YouTube, and I thought, this is some very bizarre and esoteric stuff, and this is kind of what attracted me to FP in the first place. And I guess it can go even farther than I knew about. So I was very excited that he agreed to join us this evening to share with us some of his ideas and his work. If you have questions during the talk, you can type them into chat, but I think actually Deech wants to make it somewhat interactive tonight, so I will just do my best to support him. And Deech, it's really nice to have you. Thank you so much for taking the time, and I'm really looking forward to this. I'm just gonna hand it over to you, and you can share your screen and take it away.
Sounds good. Okay. By the way, thank you everybody for joining, and I hope you have a good time. Can everybody see that? Can I get at least one confirmation?
Yes.
Perfect. And everybody can hear me, I suppose. So let me just get started. So my talk today is on why linear types are a really good idea for systems programming. And to do that, I'm going to talk about maybe like the only language that brings a whole bunch of concepts together, including linear types, which is the ATS programming language. It is an ML, so standard ML, not machine learning ML. It has linear types, refinement types, it has dependent types, and like the branding is it's as fast as C, right? So you can get that blazing fast like branding on this language. But the reason it does that is actually more interesting than why it's faster. So why it's faster is more interesting than it is fast, which is that there's a whole bunch of type level madness, right? But there's almost no optimizations on the compiler level itself. So it's not, it produces C, but it doesn't like optimize that C in any way. Like it like optimizes tail calls and a couple of other recursion things. But aside from that, there's nothing really going on under the hood that would make that C code any faster. It's just all this type level stuff gives you the control to write fast code. So like blazing fast is, I'll show you why that's kind of a weird thing to say about ATS. It was created by a professor at Boston University. His name is Hongwei Ji. Super nice guy. I've interacted with him a few times on the ATS mailing list, and always responsive, always very nice, and willing to answer questions. So the ATS programming language, as Stephen mentioned, is really hard. It is probably the hardest language I've ever learned in my life. I've learned a few, and this is the hardest. And it's also, because of that, it's also very hard to present. And this should be somewhat expected. It's a research language, right? It's written at Boston University under grant funding with the idea of promoting programming language research in the systems programming area. So it is an academic language, and it's got tons of ideas packed into it, right? And because of that, there's tons of accidental complexity. And because this language isn't really meant for like widespread use, whenever Hongwei Ji has a new idea, he just throws a new keyword into the language, right? So it's not like, you know, there's any sort of keyword reuse or like attempts to keep the grammar small or anything like that. There's also zero documentation, pretty close to zero documentation. What is there is basically what he uses to teach his course, which uses this language. But that's okay. Like, that's not a problem, because I believe that, especially in a situation like this, the academia side has done its job, right? It's presented new ideas and shown that they could possibly be useful. And it's our job as a sort of industrial sort of software developers, if you will, to take those things and make them usable. So I don't think that it's a horrible idea to have a sort of a language that doesn't look very good, but we have to be able to take those ideas. So the goals for this talk today are not evangelism. Please don't come away with this talk thinking, I would like you to use ATS for your next programming project or bet your business on it. That is not what I'm trying to say. What I want is, if you are a user of systems programming languages or any programming languages, if you are a user, I want you to be dissatisfied with the current state of the art. Because this language brings in ideas that should be in the current state of the art but are not. And if you're a language designer, I would like for these ideas to influence your next language. Or I would like you, some of these ideas, a subset of them. Don't take all of them and cram them into a new language. That would be bad. And because of all of this, ATS is a very difficult programming language to present because it pulls in a ton of context. So it converges linear types, dependent types, refinement types, standard ML, C, all of these things kind of come together in this weird mishmash. So what I'm going to try and do today is present a couple of concrete motivating examples as to why you would want to use ATS, but with a whole bunch of hand waving as to like the specifics of syntax and things like that, right? So if I gloss over like, a certain character or like a phrase, just go with me on it and don't worry too much about what it exactly means. If you really want to know, well, ask me after and I'll be happy to explain to you. So because of all this context, I'm sort of assuming some base level of comfort with ML-like languages, even Scala, Haskell, things like this, and some basic C. I don't consider myself a C expert, but like just an understanding of pointers and bumping pointers and pointer arithmetic and things like that. And so to start off, since this is an academic language with basically two sides, there's an ML side and then there's a C side, I would like to present both at once, or both as part of an introduction, and it will get fairly advanced after that. So I apologize if I lose some of you. Please let me know if I do. So first, the ML side. This is an option type in ATS. Option is the same as a maybe type in Haskell. So there's a whole bunch there that you've probably never seen before. But this form might look a little more familiar, right? It's just a sum type with a sum type with a sum branch and a none branch. Hopefully you've seen this many times before in functional programming. On top of that, this sum type is indexed by a type level Boolean. That's what that true there means. It is a sort level type. That means it's a type above a type, right? And so this is all happening at the static level. None of that makes it into the runtime, right? And I'll explain all this going forward. And it is parameterized on a view type. This is what is the linear type of like sort of the linear type part of ATS. And again, I'll explain that going forward. And a little tip that you might want to know about data types in ATS is all algebraic data types are also generalized algebraic data types. If you don't know what a generalized algebraic data type means, just ignore what I just said. If you're a Haskell person and you know what that means, it's just a little tidbit. It's not going to make this easier or harder to understand. And here is a linear C array. This is another way of specifying data types in ATS. So again, a lot of syntax, but at the end of the day, it's really just a pointer, the same as you would in C, a pointer to a thing, a pointer at a location. And it's parameterized on a view type, which is linear, and a static size. Actually, this should be a size T. There's I would say, a mistake in the standard library where it's indexed on an int as opposed to a size T. But in any case, that's fine. Oops. And it returns an existential address type. That means it's unknown. So when you create an array pointer, there exists an address for which this like view type and size like makes sense. So if that makes any sense. And I know this is not clear, but that was just a taste of the ML side. And as it becomes clear, there's tons of type level concepts to learn, and we'll get to some of those later. But Now I wanted to introduce it from the C side. Okay, this is the part where I'm going to ask the audience. I don't know how well this is going to work over Zoom, but I'm going to give it a try. So this is just plain old C code. Which resources are being leaked right now in the C code? Can anybody chime in? I guess if Steve wants to read off chat, that's fine by me. Okay. Well, I don't hear anything.
Someone has guessed I
Okay.
and FP.
Yep. Very good. Well done.
A couple of people actually. 3 people have guessed that.
Okay. So we're leaking memory because we're allocating an integer and not cleaning up, and we're leaking a file descriptor because we're trying to open this file called test.txt and we're not closing it, right? So like, yeah, this is a small program, and yes, all this stuff is returned to the operating system at the end of this program. That's not really the point. We want to make sure that even in larger programs, all of these things are taken care of. So this is the corresponding ATS program. Again, a lot of stuff going on, but if we remove all of the type level things, what we get is something that looks a whole lot like the C program. You're allocating a thing, you're setting a pointer, you're opening a file handle, right? But it's also making you free that memory and close the file handle. And that's what ATS brings. This is why ATS is fast. And it is also why I kind of balk at the idea of like selling ATS as a fast language, because it's not really doing anything. It's letting you write the same stuff. It's giving the same amount of control that you would have in C, but like putting all of this like type level stuff around it to make sure that's safe. So is that really fast? Because this is the same code. This would run as fast as the C code. If you compile this and took the C code and the corresponding straight C code and put them through like the Godbolt compiler, or the Godbolt compiler explorer, you should get relatively the same like assembly language. So the way linear types work, we start here. We have malloc, right? It's allocating some memory, but it's also producing this linear type, PF. Now, in order to set a pointer, right, you need to pass that PF to pointer set. Otherwise, the compiler will complain. It's because pointer set is a function that expects a linear type that shows a linear proof that shows that there's some memory that's allocated. It consumes that and produces another linear type, PF set. The same with fopen. When you fopen that file, it produces a linear type, PF file. Now, what would happen if these two were deleted? F free and F close. So what would happen is that PF set linear type would be left unconsumed at the end of the program, as would that PF file. And as far as ATS is concerned, that is a type error. That is a compiler error. It just won't compile if that happens. So in order to consume that PF set, we use free. That goes ahead and consumes that and frees that memory, presumably. And fclose will consume the linear type from opening a file. And that's it. So linear types at a very high level, I know that there's more rigorous definitions of this, is just generalized resource tracking at the type level. And you can write all of your code this way. Like you can sort of port all of your C code line by line in this way. You will have the same problems as you have with any imperative language with like reasoning about state and all this stuff, but this will be safe from like buffer overflows and pointer bugs. And ATS provides sugar, so you don't have to keep passing proofs around. So you can write basically C in ATS and get that and get those benefits. And one other thing that I really like about it is because you can do that, you reuse like decades of like design ideas that you've had. Like you don't have to sort of reconstruct your entire program the ATS way. You have to learn a ton of stuff on the type level, but at the term level, you can just incrementally port your program or not. Just write it all in a C style if that's what matters to you. I mean, obviously you're not benefiting from like sort of like, big functional programming or whatever, but that doesn't matter. I mean, there's no shame in writing ATS in exactly that way. So now I want to get to sort of the first big example. Doesn't seem like a big example, but it really is, because it touches tons of concepts. So what I want to do is I want to read a number from the user between 1 and 10. And then I want to allocate an array of that length, right? So if the user types in 5, it's allocate an array of like 5 integers. And then fill it up with like a bunch of numbers, 0, 1, 2, 3, 4. And then print that to the console and then exit. That's the program. Like, again, a very small program, but it gets pretty deep in the weeds. So this is the overall structure of the program. So you have a function that reads input. You have a function that makes an array. And this is how you declare the main function ATS. It's asking the user, hey, what is the length of your array? Please only enter things between 0, 1, and 10. And it reads the input, and the input gives you back some kind of option type. And if it's a none, then you say it's not a number. If it's, the same stuff. We're all used to this stuff, right? Then it checks if it's between 1 and 10, and if so, it makes the array and all that. So that was the simplified structure. This is the more complex structure. In order to call make array, you have to satisfy all of these constraints. So this was the simple one, and this is how it actually looks in ATS. So what this is saying is that make array will expect a length argument of type integer, of sort integer, such that that integer has to be between 1 and 10. So that means at the type level, ATS has to be satisfied that the integer on which this integer is indexed is between 1 and 10. That's called a refinement type, as far as ATS is concerned. And it returns a pointer to some address. Now, again, this is the existential type. It doesn't know what address it is. There exists an address such that this array pointer works. And the array pointer is parameterized on the type of the thing inside of it, which is an integer. It's a pointer address L, and it's of length n. And we already know that n is between 1 and 10. So it returns an array at some location between 1 and 10. And it's being called here. So inside of our main function, we pattern matched on our none and our sum, and then we check that the length is between 1 and 10, and then we call it. Okay. But how does it know? How does it know that, n is between 1 and 10? Where is that? How does it know that from this code? Nowhere does it explicitly pass in that constraint or discharge that proof. And the way it knows that is because ATS, being a dependently typed language, understands these runtime checks. So the type system understands that when you have this length greater than or equal to 1 or length less than or equal to 10, in an if statement, then it can go ahead and discharge the proof that this thing is between 1 and 10 because you have checked for it. So the runtime checks discharge proofs at compile time, and this is, I think, what I don't have a rigorous understanding of what dependently typed programming means, but I think this is what types depending on value means, is that it can do checks like this. So now anything that make array calls also inherits that refinement. Right, so you only have to do that check once, and unless you make changes, it can inherit that refinement. It can inherit a sub-refinement of that refinement. So if there was a function that this thing called that wanted to make sure that this thing was between like 2 and 7, this would just work. You wouldn't have to do anything to do that because the solver understands that a thing between 1 and 10 is the same as it will work with a thing that needs to be between 2 and 7, right? So now reading user input is actually the most interesting bit of this, because it interleaves not just like dependent types, but it interleaves basic theorem proving and runtime checks. And I think that this interleaving is probably unique to ATS. I've never seen this anywhere else. I've seen dependent types and refinement types in various languages, but this interleaving of proof level logic and runtime logic and type level logic is not something that I've seen anywhere else except ATS. So this is the simplified read input.
Deech, can I interrupt?
Sure.
There are a couple of questions I think relevant to 2 slides back. So actually, Paolo, do you want to unmute and ask your question yourself?
So on the next slide, I was wondering, why do we have both the N and LAN in this type? Can they differ? Are they different sorts or different values?
So are you asking if this int and this n can differ?
So not if LAN and int, LAN and N can differ.
So len is the name of the argument. So this is your path. So it's just like, you know, if you like in JavaScript or Haskell, if you have an argument name. So len here doesn't have any semantic meaning. It's just a symbol. And it is of type int, which is indexed on another int. Does that make any sense?
Well, what does the indexing mean? I mean, I understand the dependent type part, but why is int one different from int two? And are len and n supposed to be different at the call side or the same?
So len and so n is just I don't think I'm understanding. Can we talk about it afterwards?
Sure. Sorry, I don't want to.
Okay.
Apologize.
There's one other question as well.
Okay.
I have to ask it. If the type encodes that 1 is less than or equal to n is less than or equal to 10, do we need to check with the if? This is from Tales.
So yes, because that is what discharges that proof. So the only reason this make array here, this make array call even compiles is because you have this check up here. If you did not have that check, it would say that it didn't know how to like, it would say that there's an unsolved constraint basically that n is between 1 and 10.
Okay, thank you.
Let's see, where was I? Oops. Okay, so this was the simplified read input. It just outputs an option type of whatever it is that you're trying to read in, like an integer or what have you. So this is the more complex type. Not that much more. It takes in an A, which is of some polymorphic type, and it outputs an option of that A. What's more interesting is the body. So there's a lot of stuff here, but let's simplify it. So first we have a result, and that is a stack variable. That's what the var means right there. It means a stack variable, just like in C. This is the same as a C stack variable. That question mark means that it's now uninitialized. We're not initializing it to 0 or -1 or anything like that. It's just an uninitialized variable. And now we're filling it with user input. So this calls a function called filerefload. By the way, things in ATS are named really poorly. So in order to read from stdin, you have to use the file API and pass in a reference to stdin because stdin is a file, and it's just kind of what you have to do in ATS. And it takes in that uninitialized stack variable and fills it up with user content, right? And then it stuffs that result into a sum. Cool. So there's a problem. The problem is that result is of type uninitialized A. And now we're putting that result into a sum. And that sum requires an A, not an uninitialized A. So where is that happening? How is that happening at the type level? So all of the magic is happening with proof functions. And all of these do corresponding things to the internal proofs. It customizes your type system in place. And I'll show you how it does that in a second. And you can interleave proof functions into term level code. So this PR val does not exist at runtime. All of this gets erased away. It is just there at the proof level. So let's take a step back and look at the type signature for file ref load. It's pretty scary, but cleaning it up, it's not that bad. It takes a reference to stdin, which is the file reference. It takes in an uninitialized stack variable. This is the same as an L value in C, and that's the syntax for it. It is a reference to an uninitialized thing of type A. And it outputs a Boolean that is indexed with a static Boolean. Just like the integer was indexed with a static integer, we have a Boolean that is indexed by a static Boolean. So if the file reads, if the stdin read succeeds, then it will return a true that is indexed with a static level true. If it fails, it will return a false that is indexed with a static false. And I'll talk about what that means in a couple of minutes. And then the linear proof that there's an uninitialized static variable being passed in is transformed into a proof that there's a tuple of an initialized A and some kind of static Boolean value. It's this thing being passed right back in here. Right? So back to our example. Now, at this point, the type of success is a Boolean indexed by another Boolean, right? The return type of file ref load. But because proofs are changed in place, the type of result has been transformed from a question mark into opt AB, which is either true or false. It doesn't know at this point. So now when you check for success, right? When you check that the success value is a Boolean true, a value level Boolean true, the result is now of type A true, because inside of the succeeding if scope, it knows that it has succeeded. So it's going to be A true and not A false. So now let's look at this proof level function, opt unsum. Again, it's scary, but it is what is called a proof axiom. A proof axiom, I mean, the keyword is called praxi. By the way, like I said, there's tons of keywords in this language. Every time he decided to do something, he added a keyword. So praxi, have fun. And this is essentially a proof level assertion. And what unsum does is it takes a proof of a tuple of some type A and true, not any kind of existential Boolean, it has to be true, and transforms that proof into one that says that A is initialized and exists. And this is a proof function. This is only happening at the proof level. So now we can stuff result into some VT because that type has gone through some set of transformations. So to recap, it's originally a question mark. Inside of file ref load, it becomes a tuple of A and some existential Boolean, static existential Boolean. And then inside of success, that static existential Boolean is now true. And then opt unsum sees that true and returns back a proof of an initialized A, as opposed to an A question mark. And opt unnone does the same thing, but on the other branch. So basically everything after we get to file ref load is completely mechanical. There's no way of writing something that's not this. Well, I mean, you could say if not success, then this thing, and you could change it that way. But semantically, you have to write code that looks like that. So all of that could have been completely synthesized. And I think languages do that now. So basically, at this point, I could just hit a hotkey on my editor and have all of this filled in if the language supported that. So let's take stock. First, dependent types are cool. I don't think that's news. But I also think that like interleaving proof functions that can manipulate proofs in place to the way we want them are a game changer. Right? All of these PR val things. There's no runtime cost to it. I'm sure there's a compile time cost. But I think that's a feature worth adopting. And I would like everybody now to just sit back and breathe and relax and observe the absolute galaxy-brained long con that is being perpetrated right in front of your eyes, which is that we have a language with linear types, dependent types, refinement types, interleaving proof functions. And the thing that ties it all together is Go-like error handling. We're back to runtime checks, right? The same here. These checks are not all that different from like Go style if error not equal to nil, do this other thing, right? So like the only difference is that we have a language that can turn those checks into discharging like static constraints. It's the only difference. So moving on, I'm about to move to another topic. Are there any questions?
I don't see any questions in the chat, but we can give people a few seconds. While we're waiting, I'm just curious, how did you get into ATS and how did it become your life's work to translate it for the rest of humanity?
Well, I got into ATS because somebody else translated it for me. And that person's name is Chris Double. He's a smart guy. He lives in New Zealand and he wrote a whole bunch of blog posts on ATS, which really caught my eye a few years ago. But I also noticed nobody else was talking about it, so I decided to talk about it.
Looks like Vlad has a comment. Vlad, if you want to unmute, you can make your comment or question, whatever it is.
Right. So basically, listening to it, I was always thinking, okay, Rust has linear logic inside, but it doesn't have dependent types as far as I remember. So can you compare like advantages, disadvantages, and for practical developers, the impact of all these differences?
Of the difference between dependents and
no. I mean the difference, like differences with Rust programming language, which also has at least linear logic, right?
Yeah, it does have linear logic, but it doesn't have any of that proof interleaving stuff. So you don't have sort of first-class access to your type environment in the same way that ATS allows you to do that.
Right.
So basically, a lot of what I'm showing you now that you can do for yourself has to be provided at a language level for you in Rust. And no doubt about it, Rust is actually a much more practical language for developers today than this is. But I'm presenting this because I'm hoping that like the next time you see a systems programming language, you will sort of maybe filter it through some of these features. And if you're designing one, maybe adopt some of this stuff.
I see.
Okay, and Hamid has a question as well.
Sure.
Yeah, go ahead.
Yeah. Hey, so basically you had a proof variable, if I could tell correctly. So in the main code, you had PR val. And could you explain what was the point again here? Yeah, exactly that. Because you didn't use it. Yeah.
So why do we have this line? Is that what you're asking?
The PR val itself, that's it.
Oh, PR val is a proof value. So instead of val, it's PR val. And the the open close parentheses means it's returning a void thing. So basically, it means that at the proof level, this thing is having a side effect. This would be just like if I went val open close parentheses equals, I don't know, like email password to a password file to somebody. This is just a side effecty thing, but it's only happening at the proof level.
So is it some sort of a keyword of the language?
Oh yeah, yes it is.
All right, that's it.
All of these things, there's so many keywords. There's a 1, 2, they're like, if you look at the list of keywords, you know, it's there's maybe 145 or 200 of them at this point.
All right. Okay, thank you. Cheers.
Okay, should we do one more question? Is that okay?
Yeah, go for it.
Okay, Andor has a question. Go ahead, Andor, if you can unmute.
Yeah, hi. So how manipulating proof object is different than dependent pattern matching in languages like Agda?
I don't know Agda.
Okay. So like in Haskell, when we match on a GEDT and we add an extra constraint to the constraint solver, something similar happens here?
Yes, but okay, so I'm glad you mentioned that because I'm going to show you an example later on that shows you why this is different or is more powerful than the Haskell GADT constraint solver, sort of the whole closed type families of like of type equations thing. So this was just an initial example.
Okay,
so
thank you very much.
I will talk about that in a second.
Okay, thanks for your questions, everyone. I guess we should move on now. Thanks, Deech.
Okay, yeah, sure. So as I mentioned before, we have all these PR val things. And I think that being able to manipulate proof terms, essentially as first-class citizens, is a game changer. And I'm going to present an example of this, where you basically use this to statically avoid data races. So for concurrency logic. So things that are given to you at a language level in say Rust are available to you here in userland. You can just make them for yourself. So let's start off with a basic premise. Given a proof that there's an array of some length L and some static index I, not a runtime, not a dynamic integer, a static integer, the thing that the integer is indexed on. We're going to take that and be able to split that proof of an array into two subproofs, right? That there's an array going from, say, 0 to like 5 and another array going from like 5 to 10 in an array of like length, I guess it would be 11 at this point because 0 based. And then we can give each thread one of those two proofs. And now we've statically made it so neither thread can stomp over the other thread because they don't have a proof for anything except for that section of the thread, that section of the array that they're supposed to be able to manipulate. So we can emulate slices this way. And this is what it looks like. I have a proof function. That's what prfun stands for. Like I said, there's tons of keywords. It's just like praxi and prval and all of these things. This is a function that only operates on the proof level. It's called split. And it takes some proof arguments, not dynamic arguments, static arguments. It takes a proof that there's an array of some type A at some address L of some length n. And it also takes a static natural argument, again, static, such that I is less than n. So it's taking in, at the proof level, it's taking the proof of an array, and it's taking in some I that has to be less than the length of the array. That's statically proven to be less than the length of the array. And it returns two proofs. It returns a proof that there's an array of length I starting at address L, and returns a second proof that there's an array of length n minus I, so from I to the rest of the end of the array, starting at the pointer address L plus the size of each element I times. This is almost precisely what you would do in C to get to a point in the array, and it's of type A. And so how does it do this? Well, there is a proof level language that analogs the term level language. And it's got like things like SIF for static if. So what this is saying is that if the static I that you pass in is greater than 0, it can be proven to be greater than 0, then deconstruct the array. Get me the proof of the head and a proof of the tail of the array. And array v cons is just another praxis, just like opt unsum that we used before. And it takes a proof of an array at some address L of some length n, and it gives me back a proof that there's something of type A at that address. That address L points to something of type A, and there's another array of type A at from the first element onwards. So this is basically sort of a head-tail deconstruction that at the proof level that you would do every day in a functional programming language, where you go case list of x colon xs. That's what this is doing at a proof level. That's it. So now that we've reconstructed it into a proof that there's something at address A, at address L, and the rest of the array, I can pass that back in recursively to split. Right? The proof that there's the rest of the array. And at the proof level, I can reconstruct those two sections back. Like there's a, like taking the head of the initial thing that we deconstructed and the rest of the split and sort of the rest of the head of the split and consing that on to the tail of the split. If this is confusing, it's because it's operating on a proof level. You would do pretty much the same thing if you had to do this at a value level. There's not much difference in the logic. And if the first section is empty, then just pass back in a nil as the proof of that first array and the original array as proof of the second. All right, so if you pass in an array and you say I want index 0, that would just be an empty array and then the rest of the array and the original array, right? And so in this way, you can have a function that PR vals the proofs and then passes the two things to two different threads. So if you have you call that proof level function split, and you pass in the proof of some array that you passed in, and then it hands you back two proofs. Oh, that should have a corresponding, that should have a corresponding I forgot about that. And then you can take that first section and pass it off to thread 1 as proof of thread 1, as a proof of an array to thread 1. And you can take that second section and pass it off as a proof of an array to thread 2. So that means that because neither thread 1 nor thread 2 have access to each other's elements, they can both work in parallel, and you will not have data races. And that's just the tip of the iceberg. So that was my final example. So proof functions means that you can have very customizable type environments. So you can change proofs in place. Could be dangerous, but it's also a good thing to have. Dependent types means that you have much easier domain modeling. I've grown skeptical of the idea that simple sum types are all you need for software development. I think that we need something one level higher, at least, than simple sum types. And it also means that linear types, with linear types, you can have basically bulletproof resource tracking, unless you manipulate the types by yourself, in which case you don't. You can always do unsafe things. But if you produce and consume the linear types as they're meant to, you will always close your file handles and free memory and all that stuff. And I think all of these are great ideas. ATS is a great proof of concept that these ideas are at least worth exploring. And I think that one of the other things it does is steadily pull back the veil. So every language designer, everybody who implements a language, understands this idea of proof terms. But for most languages, they're kept internal. So they're considered sort of an advanced topic that shouldn't be exposed to sort of workaday developers like us. I think that ATS shows that we're ready for them. And sort of the progression of language features over the years has shown that it's basically a lot of sort of pulling back the veil on a lot of internal features. So like how ADTs became GADTs. There wasn't much of a change. I think that GADTs were how ADTs were represented internally before they were exposed to the user. And the engineering problem with all of this isn't so much coming up with type level concepts, but it's how to present them. The user experience and the developer experience are absolutely paramount. This is our problem. This is the engineering problem. Not so much actually coming up with the stuff. And in any case, that's what I had. Thank you for your time, and I'll take any questions.